right, so now we're at the point in the semester where single units are going to be way too simple for what is actually present in industrial systems. So whenever we look at industrial chemical processes or real-world environmental engineering systems, they're always going to have more than one unit. So what we're going to do is we're going to define a system as any portion of a process that can be enclosed within a hypothetical box or boundary. So when we have multiple systems or we have multiple process units, what we do is we draw a boundary around each specific thing so that we can analyze one of those systems at a time so that we can find the things that we need. So inputs and outputs to a systems are the process streams that intersect the boundary. So the best way to explain this is to show you an example. So let's say that we have a 2-unit process. We have a unit 1 and a unit 2. We can put a boundary around the entire system. If we put a boundary around the entire system, the streams that cross that boundary are the 3 on the bottom, the 1 on the right, and the one on the the one on the left and the one on the far right. If we put a boundary around unit 1, there's 1 stream that comes in and 2 streams that leave. So putting different boundaries in the system is going to be important. So we're going to take this same flow diagram and we're going to look at each of the different boundaries. So there's a boundary A, which is the whole system, boundary B, which is called a mixing point, boundary C, which is on unit 1, boundary D, which is a splitting point, and boundary E, which is on unit 2. And let's talk about each of those. So A is the entire process. It's the inputs, streams 1, 2, 3, and the products, streams 1, 2, and 3 on that particular flow diagram. B is what's called a mixing point. 2 streams are coming together, not necessarily in a specific unit, but we have stream 1 and stream 2, and the product is just the stream 1 that goes into unit 1. So we've got to be very careful there. C is just unit 1 by itself, so we just draw a box around unit 1. D is a stream splitting point. So a splitting point means 2 things diverge from one common point of origin. And then unit 2 is going to be specifically just that process unit for unit 2. With boundary A, the stream from unit 1 to unit 2 is called internal. It doesn't affect the overall balance. So if we're drawing the boundary, it's only the arrows that cross the boundary that are actually being evaluated in that system. So the unit stream that goes from unit 1 to unit 2 does not cross the boundary at A, therefore it's what we call internal to the system. Only at that boundary A, where we have the full systems, do we have overall balances on the complete system, and that's important. So when we do multi-unit processes, it's the same kind of procedure as for single units, but we have to think about a couple different things that are slightly different. One of the key differences is that we need to isolate and write balances on several subsystems to have enough equations to solve. So if we just write a balance on the entire system, we will not have enough independent equations to have enough degrees of freedom to solve the problem, which means that instead of just writing overall balance on species A, balance on species B, we need to write balances on unit 1, unit 2, splitting stream 1, mixing point 1, and all of those are going to get a little bit more complicated as we go. So many times for these particular problems, this is why we've learned how to do a degree of freedom analysis, because there are going to be so many equations and so many processes going on in this system that we really need to think about, do we have enough information to solve? That's going to be it for just some basics on multi-unit processes. We're going to start solving some examples of these in the upcoming pre-lectures.